Hello, science fans! Today we're diving into the amazing world of the internet. It's a place full of websites and applications, all living together. But how do they stay safe? How do they make sure that a sneaky website can't just reach over and steal information from another? The answer involves a very cool system called Cross-Origin Resource Sharing, or CORS. Think of it as a set of rules, like a neighborhood watch program for the web. It helps websites decide who they can trust and who they can share their resources with. It's a fundamental part of keeping your online experience secure and functional. Now, you might be thinking, Bill, what does sharing resources even mean? Great question. A resource can be almost anything a website needs to work. It could be data, like your user profile information. It could be a font that makes the text look nice. It could even be a script that adds a cool animation to the page. Websites are constantly asking for these resources from different places. CORS is the mechanism that stands at the gate, checking the ID of every request to make sure it's coming from a friendly neighbor and not a stranger with bad intentions. It's all about controlled, secure communication. So, why is this so important? Well, imagine you are logged into your online banking website in one browser tab. In another tab, you accidentally visit a malicious website. Without any security rules, that malicious site could try to send a request to your bank's server, pretending to be you. It could try to transfer money or steal your personal details. This is where the browser's security model, which includes CORS, steps in. It provides a standardized way for servers to say, hey, I know this other website, and I give it permission to access my data. It's a security feature, not a bug. Essentially, CORS is a conversation between a web browser and a server. The browser says, hey server, this website over here wants to access your stuff. Is that okay? The server then looks at who is asking and decides whether to grant permission. If it trusts the website, it sends back a special message, a header, that tells the browser, yep, this one's on the list. Go ahead and share the resource. If not, it denies the request, and the browser blocks it to protect you. This negotiation is what makes the modern, interconnected web possible, allowing for rich applications while keeping our data safe. Consider it. To really understand CORS, we first need to talk about its parent, the same origin policy. This is a super important security rule built into every modern web browser you use. It's like a strict rule in your house that says you can only play with toys that belong in your room. You can't just go into your sibling's room and start grabbing their stuff without permission. The same origin policy works the same way for websites. It dictates that a script running on one web page can only request resources from the very same origin. This simple rule is a cornerstone of web security, preventing all sorts of chaos and mischief online. So, what exactly is an origin? It's like a website's unique address, and it's made up of three parts. First is the protocol, which is usually HTTP or HTTPS. Second is the domain, or hostname, like billney.com or science.org. And third is the port number, which is often hidden but is part of the address, like port 80 or port 443. For two websites to have the same origin, all three of these parts must match exactly. If even one part is different, say http://mysite.com and https://mysite.com, the browser considers them to be from different origins. It's that specific. This policy acts as a powerful default bodyguard. When you're browsing, it silently protects you. For example, if you are logged into your favorite social media site, social.com, the same origin policy ensures that a script from another site, evilsite.com, cannot make a request to social.com and steal your private messages or post on your behalf. The browser sees that the request is coming from a different origin and blocks it flat out. This happens automatically, without you ever needing to click a button or check a box. It's a silent guardian, a watchful protector. Of course, this strict rule can sometimes be a little too strict. In the modern web, it's very common for different parts of an application to live at different origins. Your user interface might be on one server, and the data it needs might be on a completely different server. The same origin policy, by itself, would block these parts from talking to each other, which would break the application. This is precisely the problem that CORS was invented to solve. It provides a way to create a safe and controlled exception to the same origin policy, allowing trusted origins to communicate. Let's look at a very common real-world science experiment. Example. Imagine a team of brilliant developers building a new web application. They decide to build the front end, the part you see and click on, using a popular framework like React. They host this front end at the address https://myawesomeapp.com. This is our first origin. It's a beautiful, user-friendly interface that needs to display data, like a list of amazing science facts. But where does it get those facts from? It needs to ask a server for them. Now, for the backend, the brain of the operation, the team uses a powerful technology like .NET Core to build an API. An API, or Application Programming Interface, is just a way for programs to talk to each other. This API is responsible for storing and managing all the science facts in a database. For performance and organization, they decide to host this API on a different server with a different address, say https://api.myawesomeapp.com. This is our second origin. Notice that even though the domain looks similar, the API part makes it a different origin from myawesomeapp.com. Here comes the problem. When a user visits https://myawesomeapp.com in their browser, the React application loads and immediately tries to fetch the list of science facts. It sends a network request to https://api.myawesomeapp.com. But wait, the browser, following its strict same origin policy, looks at the request and sees that the origin of the web page, myawesomeapp.com, is different from the origin of the API, api.myawesomeapp.com. The browser's internal security alarm goes off. It blocks the request to protect the user, even though both parts belong to the same application. The result? The front-end application receives an error instead of the data it needs. The list of science facts remains empty, and the user is left staring at a broken page. The developers check their browser's developer console and see a scary-looking error message, cross-origin request blocked. The same origin policy disallows reading the remote resource. This is a classic CORS issue. The browser did its job correctly by enforcing the security policy, but now the application is broken. The two origins need a way to get permission to talk to each other. They need a secure handshake protocol. This is where cross-origin resource sharing, or CORS, makes its grand entrance. CORS isn't just one thing. It's actually a whole system of communication that uses special HTTP headers. These headers work kind of like secret passphrases, letting a server tell a browser, hey, it's okay to share resources with a website from a different origin. It's the official and secure way to create an exception to the same origin policy. So instead of the browser just blocking the request, CORS actually initiates a negotiation. It gives the server that holds the resources the final say on who gets to access them. Let's go back to our example for a second. The React frontend at myawesomeapp.com wants to get data from the .NET API at api.myawesomeapp.com. When the front end makes its request, the browser automatically adds a special header called origin. This header simply states where the request is coming from, kind of like a return address on a letter. In this case, the header would be origin https://myawesomeapp.com. The request then travels across the internet to the API server, carrying this important piece of information with it. Now the ball is in the server's court. The .NET API server receives the request and sees the origin header. This is where the CORS configuration on the server becomes absolutely critical. The server checks its list of approved origins and asks itself, is https://myawesomeapp.com on my list of friends? If the server has been configured to trust this origin, it will add a special header to its response before sending it back. This header is access control allow origin, and its value will be the origin that's being granted permission. For example, access control allow origin, https://myawesomeapp.com. When the response travels back to the browser inspects the headers before handing the data over to the React application. It checks for the access control allow origin header. If that header is present and its value matches the website's own origin, the browser knows the server has given its blessing. Hooray! The handshake is successful. The browser releases the data to the front end, the list of science facts appears, and the application works just as intended. But if the header is missing or the origin doesn't match, the browser still blocks the request, and you get that familiar CORS error. It's security and functionality really working together. Out of the box, for safety, a brand new .NET Core API is very cautious. It's like a house with all its doors and windows locked. By default, it doesn't have CORS enabled. This means if you create a new API and try to call it from a different origin, even from a simple HTML file on your own computer, the requests will be blocked. This is actually a good thing. It's a secure by default approach, and it forces you, the developer, to consciously decide which external websites are allowed to interact with your API. You have to explicitly create a guest list. To set up this guest list in a .NET Core application, you define something called a CORS policy. A policy is just a named set of rules. In your application's startup code, usually in the program.cs file, you can specify exactly which origins, HTTP methods like GET, POST, or PUT, and headers are allowed. For example, you could create a policy named Allow My Web App that specifically allows requests only from https://myawesomeapp.com. You can get very specific, saying that this origin is only allowed to use GET and POST requests, but not delete requests. This gives you fine-grained control over your API's security. Once you've defined your policy, you have to tell your application to actually use it. This is done by adding the CORS middleware to the application's request processing pipeline. Think of the pipeline as a series of checkpoints that every incoming request must pass through. You need to place the CORS middleware early in this pipeline, typically before the checkpoints that handle things like authentication or routing. This way, the CORS check happens before the server wastes any time processing a request that's just going to be denied anyway. It's a really efficient way to handle visitors right at the front door. So let's trace the journey of a request. A request comes in from a browser. It first hits the .NET Core server and enters the middleware pipeline. One of the very first stops is the CORS middleware. The middleware looks at the request's origin header and then checks this origin against the policies you've defined. If it finds a policy that allows this origin, method, and headers, it adds the appropriate access control allowance on headers to the response and passes the request along to the next checkpoint. If no matching policy is found, it immediately stops the request and sends back a response that'll cause a CORS error in the browser. It's a clear, step-by-step process. Not all cross-origin requests are created equal. The CORS standard actually divides them into two categories: simple requests and complex requests. A simple request is, well, simple. It meets a strict set of criteria. For example, it can only use the GET, POST, or HEAD methods. Also, it can only include a few specific headers. And if it's a POST request, it can only send data in certain formats. If a request meets all these conditions, the browser can just send it directly to the server, and the server just needs to reply with the access control allow origin header for it to succeed. It's a quick and easy visit. However, many modern web applications need to do more complex things. They might need to send a delete request to remove data, or a PUT request to update it. They might also need to send custom headers, like an authorization header containing a security token. Any request that uses these methods or includes custom headers is considered a complex request. For these, the browser takes an extra safety step before sending the actual request. It sends a preliminary request, called a Preflight request, to ask for permission first. It's kind of like calling ahead to make sure it's okay to bring a friend to a party. This Preflight request is an HTTP request that uses the options method. It doesn't contain any of the actual data from your main request. Instead, it carries headers that describe the real request that's about to come. For example, it'll have an access control request method header telling the server the method of the actual request, like delete, and an access control request headers header listing any custom headers it wants to send. The browser then waits for the server's response to this options request before moving forward. It's a formal introduction. The server receives this options Preflight request, and thanks to the CORS middleware, it knows exactly what to do. It checks its CORS policies to see if the proposed method and headers are allowed for that origin. If they are, the server sends back a successful response. This response won't contain any application data, but it will have the important access control allow origin, access control allow methods, and access control allow headers. These tell the browser, yes, I approve of the request you described. You may now send the actual delete request. The browser, now confident that the request is allowed, sends the real request, and the process continues. This two-step dance really ensures maximum security for potentially risky operations. As we've seen, CORS is an incredibly useful tool. But, with great power comes great responsibility. One of the most common mistakes developers make is getting frustrated with CORS errors and then setting up a policy that allows any origin. This is often done by setting access control allow origin to a wildcard asterisk. While this will make the errors go away, it's honestly like leaving your front door wide open for anyone to walk in. It completely defeats the purpose of CORS as a security feature. In a production environment, you should always be as specific as possible, listing only the exact domains you trust. Another best practice is to be precise with the methods and headers you allow. Don't just enable all of them. If your front end only needs to make get and post requests, then only allow those methods in your CORS policy. This principle of least privilege is a key concept in security. By only granting the minimum permissions necessary for your application to function, you reduce the potential attack surface. Also, be really careful when dealing with requests that include credentials, like cookies or authorization headers. This requires setting the access control allow credentials header to true, which comes with its own set of strict rules. Many developers spend hours troubleshooting QRS issues. A common problem is misconfigured middleware order in .NET Core, or even a simple typo in the allowed origin URL. Remember, HTTP is different from HTTPS. Understanding the full request-response flow we've discussed is your best debugging tool. Use your browser's developer tools to inspect the network tab. Look at the options Preflight request. Is it being sent? Is the server responding correctly? Look at the headers on both the request origin and the response. Access control allow origin. The clues are almost always there if you know where to look. In conclusion, cross-origin resource sharing isn't just an obstacle to get around. It's a fundamental pillar of modern web security. It lets us build complex, distributed applications where the front end and back end live in different places, all while protecting users from malicious actors. By understanding what an origin is, how the same origin policy works, and how CORS provides a secure handshake, you can build better, safer applications. It strikes a beautiful balance between security and flexibility, making the interconnected web a more functional and safer place for everyone. The science behind it is just, honestly, remarkable.